So in this video, I want to go through what finite element method is and the basics of it, like how it um, come into play when we're talking about integrals, and then we are going to talk a little bit about higher dimensional meshing. So when we are solving some integral, for instance, this given integral from a to b of f of x dx, right? So one way to solve this is using analytically, but most of the time such solutions uh, don't exist or are hard to compute. So to find g of x, uh, we would like to use a numerical method, and for that we need to change integral to summation, because integral is a little bit abstract thing for computers. On the other hand, sums are not. So we can convert this integral to this summation easily, right? Using Riemann sum. Each part of delta x width, and these parts are infinite. There are infinite amount of these parts, right? So what this sum does is that it divides the function into infinite parts, delta x's, right? And so the property of delta x is that it tends to 0, so you can uh, evaluate the function there. And so to get the value of g of x, all you do is find the area of each rectangle and sum it up, right? And so if you have heard the term meshing, so this is what meshing looks like in one dimension. This is a very simple one-dimensional case. But the problem with this kind of meshing is that uh, it is at an equal distance delta x, right? So points where there is a rapid change in slope, the value is incorrect, right? The sum is incorrect. So to handle this kind of situations, what we do is we use adaptive meshing. So the concept behind adaptive meshing is that where change in slope is the greatest, we would mesh those areas uh, differently, like smaller delta x's, and whereas change in slope is smaller, we could just use a bigger delta x size. So mathematically, if you look at it, then g of x becomes from 0 to I of f of x delta x1, right? These guys, those small delta x1, and then from I to j, like from here to here, the delta x2 is bigger, and so on, right? Like we define the mesh in terms of different delta x's. So this is called adaptive meshing, right? And it's easier to compute the value of g of x. But if you look at what we did is uh, to find the integral or to find the solution to the problem, what we did was take a mathematical function f of x and then we meshed it, right? But if it's a real world problem, so the function itself would exist in real world, so we don't need to have a mathematical representation of the function. uh, we could what we could do is find the value of that function at specific intervals and plug that in directly into uh, our computer, because for some functions or for some shapes or problems it's very difficult to find a mathematical function, right? So for instance, this line, you can find the mathematical function using spline or other statistical method, but uh, the function would be a lot more complicated. And similarly it's the case for triangular shapes or such shapes as well, because you have to use uh, integrals inside integrals to define these kind of shapes. So what we do is, instead of defining the function mathematically, we take the physical idea of that function that exists in the real world. For example, if this function exists in the real world, we somehow convert it into points, right? X and Y values, lots of X and Y values, and we give that data to computer or CAD program or some meshing program, right? And that meshing program spits up values of ij and delta x. So ij are these values, right? So if it's the duration during which a mesh size remains constant. So from I to j, this is I to j. The mesh size remains constant. Then from j to k, there's another mesh size, right? So the program spits up ij indices in the mesh distance, right? Meshing distance, and what and so we have split our integral into a meshing program which spits up some values, and then there is solver program, and solver program just computes uh, the area of that function using a uh, simple formula like this. And so that's the main benefit of meshing, and that's why we use finite element method. So it might not make a lot of sense when we are talking in one dimension, because you can easily estimate even this function, right? It's not really a function, but you can find a mathematical term for it. But in higher dimension, it becomes quite difficult to deal with complex shapes or fractal shapes. So it's better to just take a physical copy of any object and define it using points inside some program and mesh it. And so our solver will solve that problem.